Hello, everyone, and welcome to today's lecture. We will be discussing aortic aneurysms. To start off, let's talk about what we will be addressing today. First, we will look at fundamental concepts that help us to understand the basic concepts related to this cardiovascular concept. Next, we will apply these concepts in order to understand how aortic aneurysms work. And finally, we will go over a sample problem and explanation. The basic concepts that we plan to cover today are blood vessels, which include arteries and veins, and the anatomy and function of these vessels, as well as how they relate to compliance, pressure, and volume. Let's talk a little about arteries and veins. In order to understand the aortic aneurysm, we must first address where it originates from. In the human body, we have two main types of blood vessels that are responsible for transport: arteries and veins. As deoxygenated blood enters the heart, it is pumped through the lungs and oxygenated. This oxygenated blood then exits the heart to be carried to the rest of the body. Our arteries are responsible for carrying oxygenated blood away from the body, except in the pulmonary artery. The veins carry deoxygenated blood into the body, except in the pulmonary vein. The pressure of the blood entering the heart will be different compared to when the oxygenated blood exits the heart. So thus, arteries and veins must adjust to these differences through their structure and function. Factors that affect these characteristics are concepts such as anatomy and vessel compliance. The anatomy of an artery compared to a vein has several differences. Veins can be thought of as a volume reservoir. They hold large quantities of blood, while arteries withstand high pressure in order to carry blood to the rest of the body. Vessel compliance, or capacitance, provides a measure of how much volume it can hold in relation to pressure. In the cardiovascular system, a higher compliance indicates that a great deal of volume can be held with minimal increase in pressure. A higher compliance means thinner walls, larger lumen, and the ability to distend to hold larger volumes. In order for veins to have a higher compliance, their anatomy must also be less elastic than arteries. This is because arteries must withstand a high pressure. They are made up of more elastic fibers and also have thicker walls. Arteries do not need to hold high volumes of blood, so an increase in volume will result in a greater increase in pressure than what is seen in veins. In conjunction with compliance and elasticity, arteries and veins have different relationships with pressure and volume. Specifically, this can be explained by the equation delta P is equal to delta V over C, where delta P represents the change in blood pressure, delta V represents the change in blood volume, and C, compliance, is the corresponding slope. Overall, we see a direct relationship between pressure and volume in both the veins and arteries. As pressure increases, so does volume and compliance. However, we see that there is a steeper increase in veins because they are more compliant than arteries. We will now address the clinical application in terms of how these concepts that we just covered apply to aortic aneurysms. First, we can study the component that aortic aneurysms affects. As the name suggests, an aortic aneurysm focuses on the aorta, which is a major artery of the body responsible for pumping oxygenated blood out from the heart into the body. The aorta runs from the abdomen to the chest, and the aortic valve that controls blood flow from the left ventricle to the aorta has 3 flaps. To recap, the aorta must be able to withstand great pressure. The pressure of the blood exiting the body is high because this blood will be supplied to all other parts of the body.